Today I need to tell you about how cell membranes work. I need to tell you about emulsifiers, and I need to tell you about the hydrophobic effect. And then we're going to talk about conformations of organic molecules. We're going to start with emulsifiers because you've already seen one of these. An emulsifier is something that can allow oil and grease and water, nonpolar and polar molecules, to mix together and not separate out. So if you've ever taken some you can do this experiment at home. Take some vegetable oil and water, put it in a jar, close the jar, shake it up, and they separate out. We're going to talk about why they separate out in a little bit, but right now you probably had that experience. An emulsifier is something you can put into that mixture that will allow them to stay mixed together for longer. So you already know about one emulsifier, and that is detergents or soaps, which we talked about last time. A molecule with one nonpolar tail and one polar head group can form micelles, in which nonpolar groups are packed inside in the nonpolar interior, and then the polar exterior interacts with water. And so if you take a drop of soap, I don't know why Dawn likes to make poor little ducklings greasy and then wash them. I'm not sure if that's, they're making those ducks greasy. I'm sorry. There's not a lot of greasy ducks wandering around. I don't know. Anyway, you've seen that happen. If you want to try this, a drop of soap in a container of oil and water, shake it up, and it doesn't separate out as well. That's called emulsifying. But you have some other experience with this. There are other molecules that can emulsify too. And basically, the basic principle is they just need to be amphiphilic, meaning they need to have a polar portion and a nonpolar portion. Amphi means both. Philic means love. Amphiphilic means it loves both polar and nonpolar environments. So another molecule that can be an emulsifier is a class of molecules called phospholipids. Phospholipids are derived from triglycerides biologically. They have the same 3-carbon backbone with 2 nonpolar tails, and then the third oxygen is bonded to something polar. So you'll learn in biochemistry how these things are biosynthesized. For right now, we'll just accept them as is and look at their structure. We've got 2 fatty acid tails in a phospholipid. And then the third oxygen is bonded to a phosphate group. And then that phosphate group is usually bonded to something else, and it's often polar too. So in this case, the phosphate group is bonded to 2 carbons and then a nitrogen that's bonded to 3 other carbons, and so it's got a permanent positive formal charge. This is an example of a phospholipid that happens to be called, phosphatidylcholine, and you don't need to know that name, but you'll encounter it later on in biochemistry, so I'm just giving it to you here. And you can find phosphatidylcholine in a lot of places, and sometimes this polar head group can be different than, if it's different, it's called something other than phosphatidylcholine, so there's different other head groups, and you'll learn about those later. But the overall structure is a polar head group and then 2 nonpolar tails. And these molecules can be emulsifiers too. They don't form micelles, they form something else that we'll talk about. But for now, we'll talk about how phospholipids are emulsifiers in cooking. Go ahead.
Can you remind me what a micelle is?
Micelle is this thing here.
Okay.
Yep, micelles are where the individual one-tail detergents pack against each other like this to keep their polar head groups exposed to water and their nonpolar interiors away from water. Okay, so when you go to bake cookies, often the recipe requires flour, you need some sugar, you need some brown sugar, maybe a little bit of vanilla, some chocolate chips, and you need butter. But the butter, the triglycerides in the butter don't necessarily want to play nice with water, and you need at least some water or perhaps milk in your cookies to give them the right moisture content. So getting the water or aqueous components to mix with the triglycerides is important, and so you use an egg. Eggs are a part of baking, right? Especially cookies, cake. The reason you use an egg is because in addition to being rich in proteins and cholesterol, eggs have lots of phospholipids in them, and this is one of them, phosphatidylcholine. And you can see just looking at it that it has a polar head group that can interact with water type stuff, and then a nonpolar tail that can interact with oily nonpolar type stuff. And so this can also, if you don't want to use soap in your baking recipes, and I don't recommend it, you can use egg, and that'll work too. In fact, if you want to do another experiment, take a jar with water and vegetable oil in it, then take an egg and beat it, crack it and beat the egg as though you were going to scramble it. But instead of scrambling it, just pour the scrambled egg into the oil and water mixture and shake it up, and you'll see that it doesn't separate very quickly. It forms what's called an emulsion because the phospholipids in the egg help the water and the oil mix. They sort of bring them together. There's a gospel lesson in there about being peacemakers and bringing two things that don't like each other together. I'll leave that to you to ponder. But mayo, for example, is just oil and water, vegetable oil and water blended together with egg to form this permanent emulsion. And there's some other, salt and some spices in there. I don't know that anybody makes their own mayo anymore, but hey, why? Nah. I mean, good luck. Yes?
Can you repeat how these phospholipids and molecules keep these together?
How do they keep them together? In the case of the detergents, they form micelles that can pack the nonpolar molecules inside. In the case of the phospholipids, you'll see these form different kinds of assemblies, not micelles, but something different. But again, it's just a function of the fact that you got one side that can interact with water and another side that can interact with the triglyceride. Yep, arranging themselves together so they can have both. Okay, so shape, as I've told you, matters. Shape is related to structure and function. Notice the difference between the shape of a phospholipid and the shape of a molecule that forms a micelle, or that is a soap or a detergent. The phospholipid is more cylindrical. It occupies a more cylindrical volume. So you would expect phospholipids in the presence of water to start associating with each other side by side to avoid exposing their nonpolar surface area to water. Now, I haven't told you why that is, and I'm going to. But for now, notice that as they associate side by side, because they occupy a cylindrical volume, there's not a huge amount of curvature. Oops, I need to copy. This is like really low-tech animation. There's not a huge amount of curvature to the side-by-side assembly. Contrast that with the micelle, where side-by-side assembly gives you curvature. So this is a monolayer of phospholipids, and if it didn't do anything else, sure, the polar head groups would be exposed to water, but so would the nonpolar tails. And so what actually happens is two of these monolayers line up with each other back to back and create what's called a lipid bilayer. And the phospholipid bilayer has two sides to it. It has an inner leaflet or monolayer and an outer leaflet or monolayer. The interior, as you can see, is nonpolar, and the exterior on either side is polar. Water can be on one side of the lipid bilayer and on the other side of the lipid bilayer. So we now have created a membrane. We now have something that is outside this layer and something that is inside the layer. The layer propagates forwards and backwards, side to side in 2 dimensions, but then eventually curves back on itself and you form a membrane or a vesicle. And this is the physical basis for membranes and vesicles in biology. Membranes are really important. They separate things. They are what makes you different from everything that is not you. There are membranes that create boundaries inside our cells. Mitochondria have membranes, vesicles have membranes, the cells themselves have membranes, some viruses have membranes, bacteria have membranes. Basically, it's a fundamental thing that is important for life. And membranes allow you to separate different chemical compartments in your cells. Yeah?
So are phospholipid bilayers also able to act as, not as, I guess they couldn't act as detergents, but why not?
Could they act as detergents? Yes. In fact, if you were to buy phosphatidylcholine and you were to just shake it up in a bottle of water, it would form suds in the same way that a soap would.
So could you use it as like a dish soap?
Could you use it as a dish soap? It would be expensive. And the molecular details, the molecular structure would be, the self-assembly structure would be different. The soap would tend to form micelles. This would tend to form vesicles and vesicles within vesicles, yeah.
But it can still hold like grease inside it.
But there could still be grease inside the bilayer, yeah.
It might be less effective than my soap.
It might be less effective, yeah. Okay. So that's membranes. Now we need to talk about what's called the hydrophobic effect, or why oil and water don't mix. And to do this, I need to remind you of something that we talked about last time, about 2 kinds of interactions and about the difference between ice and water. Do you remember that in ice, the water molecules are moving slowly relative to each other, that the hydrogen bonds between molecules in ice are relatively rigid, and that each oxygen is hydrogen bound to as many hydrogens as possible, whereas, and we would call that a low entropy or low disorder state, whereas in liquid water, as opposed to solid water, I can't say ice water because then you think of like this, like water and ice. I'm just talking about solid water, sorry. So in liquid water, the molecules are moving quickly. The hydrogen bonds are always present, but they're transient and exchanging. And in liquid water, there is high entropy. Okay. So to understand why oil and water don't mix, just think briefly about your jar of vegetable oil and water that you're going to go home and try. The water molecules in the water aqueous phase are moving around quite rapidly. The oil or triglyceride molecules in the vegetable oil phase are moving around relative to each other quite rapidly. Now let's imagine what would happen if a triglyceride dissolved in water. You can sometimes understand why things don't happen by considering what if they did and examining whether or not that would be energetically favorable. You will see that dissolving a triglyceride in water is not energetically favorable for a reason that will become clear to you. So to do this, what we're going to do is just draw a squiggly line. On the left side of the squiggly line is other stuff, and on the right side of the squiggly line is one of the nonpolar tails of a triglyceride. And just for illustration purposes, I'm going to fill in some, but not all, of the CH bonds in this nonpolar tail. Now, it should be clear to you that those CH bonds are not polar because hydrogen is not that different in electronegativity than carbon. So there's not a huge amount of delta plus on those hydrogens. So I'm just going to draw the structure. I'm going to imagine where the electron density is for this molecule, this nonpolar tail, okay? A lot of nonpolar surface area. And those CH bonds are not really capable of hydrogen bonding. Now, we've imagined that this triglyceride is dissolved in water, so it must be surrounded by water, but it can't hydrogen bond with the nearby water. In other words, it's taking up space in water that would normally have been occupied by other water molecules. So the water molecules in the immediate vicinity of the nonpolar molecule are not as hydrogen bound as they would like to be. They've had to give up some hydrogen bonds with other water molecules so that they can be close to water. As a result, the hydrogen bonds that they have, the remaining hydrogen bonds that they have with the remaining water molecules become stronger and more rigid. So I'm going to illustrate this with just sort of dotted lines between the oxygens and the hydrogens. What you should understand is that water molecules in the immediate vicinity of the nonpolar surface area have to slow down and strengthen their remaining hydrogen bonds because they've lost some because the nonpolar stuff is taking up space. In effect, the water molecules in the immediate vicinity of the nonpolar stuff are moving more slowly. Their hydrogen bonds, their remaining hydrogen bonds are more rigid, and they have lower entropy, which were words we used to describe ice. It's almost as though the water molecules immediately surrounding the nonpolar surface area are frozen. You've had to form this ice-like cage, and I'm just illustrating that because I don't have time to draw all of the oxygen-hydrogen bonds, but you have this ice-like cage of water molecules that surround the nonpolar surface area. Low entropy, and that process is unfavorable. Exposing nonpolar surface area to water makes the water molecules immediately surrounding the nonpolar stuff lose entropy. And as you know, losing entropy is unfavorable. Yeah?
So what was the distinction between the first the first water molecule just outside of the structure? And you said it wasn't as strongly hydrogen bound as the other ones around it?
So just remember that in water, in sort of bulk water, each oxygen has 2 lone pairs, and each of those lone pairs is hydrogen bound to another water molecule.
Oh, I see.
And the point is that once the water molecule gets close to the nonpolar, it's got to lose at least one of those.
And so it's all the water molecules directly around the molecule.
Yep.
that aren't as strong.
Yeah, all the water molecules directly around the nonpolar surface area aren't hydrogen bound as much to other water molecules. So what they do is they hold on tighter to the ones that they have left.
Okay, I see.
And then they slow down and lose entropy
I see.
for forming that ice-like cage, yeah. So it's actually favorable for the triglyceride to never go into water in the first place. And that's the origin of the hydrophobic effect. Now, I've asked questions about the hydrophobic effect on an exam before. Students that get it wrong tend to misunderstand. They'll say something like, well, the reason that triglycerides don't like to go into water is because the dispersion interactions between the triglyceride molecules are just too strong. It's not a great argument because you know that dispersion interactions are actually weak. It's also not a great argument because water can also do dispersion interactions. So what's the big deal? And the big deal is actually the triglyceride changes the structure of water in its immediate vicinity, makes water lose entropy. And so if you can minimize exposure of nonpolar surface area to water, that frees up water molecules to go back to their more disordered state. Yes?
So it's as if it's putting pressure and packing them tighter.
Yeah, it's as if that free energy difference creates a pressure almost to pack the nonpolar stuff away from water. This is important in biology because that's the foundation for, you're going to learn in 352 and then in biochemistry about proteins and protein folding and adopting specific 3-dimensional shapes, and the hydrophobic effect is a huge component of that. So again, exposure of nonpolar surface area to water lowers the entropy of the water immediately near the nonpolar surface area. and that's bad. So to avoid that, oil and water don't mix. Okay, anything else? Yes?
So if the polar end had been next to the water, we would still be able to keep the type of bonds, the not ice-like cage bonds?
Right, so what we're envisioning here is, yes, if, that's why the micelle and the lipid bilayer works, because the polar part can hydrogen bond with water. And so when water's next to this polar head group, it's not that different from water being next to water. So there's no need to slow down and no need to become an ice-like cage. Totally fine. Yep. I saw another hand. No? Yes? Yeah.
So it's about the entropy of the system,
It's about the entropy of the system. Yeah.
not specifically the possible living.
Right. It's the entropy of the system and not necessarily the entropy of the nonpolar stuff. Because you might say, well, wouldn't it increase entropy for the oil to mix with the water? You would think, but on a microscopic level, it actually makes entropy of the water molecules decrease more than the mixing would compensate for. Yeah. All right, so that's non-covalent interactions. I think we've done what? Let me just check. I think we've done emulsifiers, we've done membranes, we've done the hydrophobic effect. Okay, now we're going to talk about conformations of organic molecules. In particular, we're going to be dealing with rotation around carbon-carbon bonds. Conformations refer to different shapes of organic molecules that can interchange by rotation around bonds. And we'll talk about these, and we'll figure out a way to draw them, but it's easiest actually to do this with animations. So I'm going to bring up this molecules app, where this is a real molecular dynamics simulation of the molecule ethane, C2H6 or CH3CH3. Here's the molecule from the side. The black spheres are carbons. The white spheres are hydrogens. The molecule is wiggling. That's because the iPad is actually running physics now based on what we understand about the forces that hold molecules together. You can see that the bonds are not rigid. They are wiggling. There are bond vibrations in organic molecules. The purple that you see is an estimate of the distribution of electron density in this molecule. So you can think of that as the electron cloud. Another interesting thing is that we can turn up the temperature. And as you see, as we turn up the temperature, the molecule starts moving more rapidly. The vibrations get bigger, the molecule's moving around more. This is an example of the principle that temperature is simply just kinetic energy. So you provide more heat, you provide more kinetic energy for the molecule to move around. I'll cool it down a little bit so that we can go through this a little bit more systematically. So if you've noticed, looking at this ethane molecule, if we look down the bond between the two carbons, you see that the carbon-hydrogen bonds in the front are interdigitated or staggered with the carbon-hydrogen bonds in the back. We call that a staggered conformation, and it is a lower energy conformation than an alternative. You could imagine the alternative conformation in which the CH bonds in the front are all lined up with the CH bonds in the back. We would call that an eclipsed conformation. And I'll just try to demonstrate that. As we said, sigma bonds come from end-on-end overlap of orbitals. And when you rotate one partner relative to the other in a sigma bond, it doesn't change that orbital overlap. So you can rotate around sigma bonds. And let me demonstrate this just by grabbing a hold of one of these hydrogens, and then we'll do propeller action. And I'm going to spin it, give it a lot of kinetic energy, and you're seeing it twist, 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 twist. You're seeing it pass through times where the hydrogens are eclipsed with each other. But did you see it slow down each time as it was passing through an eclipse conformation? It's almost like we were doing Wheel of Fortune, where you spin the wheel and there's little pegs that go past the little ticker, and as the wheel slows down, you go tick, 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 and it drops into a space between two pegs. That's what's happening here as we spin the methyl group in the front. Just watch it, slowing down, tick, 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 tick. Just one more and then the other, okay? And did you see that? It almost got to the eclipse conformation and then it backed off. The reason that's going on is the eclipse conformations are higher in energy than the staggered conformations. What makes the eclipse conformation higher in energy than the staggered conformation? Turns out it's two things. The simplest to understand is electron-electron repulsion. When the CH bonds in the front are lined up with the CH bonds in the back in an eclipsed conformation, the electrons in those bonds approach more closely to each other than they do in the eclipse conformation. And as you know, electrons are negatively charged, and so having electrons approach closely is repulsive. Or that sounds like, I mean disgusting, I mean like unfavorable, right? That electron-electron repulsion is an example of something in your text that's called steric hindrance. You can use those terms interchangeably. Steric hindrance is electron-electron repulsion. Things with a lot of electrons bump into and repel things that have a lot of electrons. Its specific application of steric hindrance to rotation around a carbon-carbon bond is called torsional strain. Torsion means twisting or rotating around carbon-carbon bonds. Torsional strain refers to the fact that the eclipsed conformation is higher in energy than the staggered conformation. Okay, questions about that? Yes?
Where does the energy go? If it has a ton of kinetic energy and then it goes away, where does it go?
So where does the kinetic energy go? In this case, for this molecule, you notice that once I sped it up, it eventually settled down. Where's it going? The simulation has at the bottom, there's something called a bath. When it has a temperature on it. Basically, the simulation creates a surrounding that's a drain for extra kinetic energy. I can add kinetic energy to the system, but then it equilibrates with the background bath until it comes down to that temperature. In practice, molecules bump into each other, and that's what causes the kinetic energy to equilibrate. But this is only a simulation of one molecule, so to make it uncomplicated, that's what they do. Okay, what else? Yeah?
So, that's a question. So it looks like it won't spin because it stopped. Is it because there's not enough energy in the system for it to keep going? And then
Yes.
stop?
Yeah, that's a great question. So the question is, I allowed it to have enough kinetic energy to overcome the barrier, to get over the eclipsed conformation, but it stopped, and the reason is that it's equilibrating and going back to a lower kinetic energy. If I turn up the temperature, you'll have to watch carefully because the molecule's going to equilibrate more, going to be wiggling more rapidly. But you're going to see it start to, see there it was, it rotated, right? See it pass through another eclipse conformation. And now we're just propellering around, right? At room temperature, there is enough energy to overcome that barrier. The barrier is the difference in energy between the staggered and the eclipsed conformations. That barrier is worth about 3 kilocalories per mole or about 12 kilojoules per mole. Organic chemists prefer kcals for reasons that are difficult to explain, but who am I to fight with tradition? You can calculate how much kinetic energy you have on average at a temperature using a relationship that you may have learned, and we don't need to go through it. But basically, at room temperature, there's enough kinetic energy to get over that barrier, and so you can rotate freely around sigma bonds at room temperature. Okay, now that we've got the animation, let's just develop some tools to think about conformations, just drawing them on a two-dimensional sheet of paper. So I'm going to draw ethane in a staggered conformation. So this is carbon 1 of ethane, this is carbon 2 of ethane. And then I will draw the same molecule in an eclipsed conformation. And in the eclipsed conformation, the CH bonds on carbon 1 are going to be lined up with the CH bonds on carbon 2. It may not be immediately obvious that the one on the left is staggered and the one on the right is eclipsed. To illustrate this, we'll use something called the Newman projection. which always makes me think of Seinfeld and hello, Newman. Poor Newman. I guess he was annoying, but anyway. And we'll put our eye, and I can never resist. Like suddenly I start drawing the eye, and suddenly it's not the eye of Sauron. It could be, but this is Anakin's evil Sith eye. While he shouts, "I hate you" at Obi-Wan. And if you want to shout that at me while you're taking your test, go for it. That would be great. So you're going to put yourself in the plane of the page, look down the bond between carbons 1 and 2. We're going to represent that bond as a cylinder. In front is carbon 1, in the back is carbon 2. We can't see it. Then we're going to draw the CH bonds on carbon 1. From our perspective, looking down, the bond there between carbons, this one CH bond is pointing upward. The other two, the one that is a wedge is pointing out to our right. The one that is a dash is pointing out to our left. And then in the staggered conformation, the carbon in the back has a CH bond that's pointing downward, and then two CH bonds that are pointing upward. This hydrogen here, the one I'm highlighting in blue, is anti-2 or 180 degrees away from the other hydrogen in blue. So the angle in the Newman projection between these two lines is 180 degrees. We call that a torsional or a dihedral angle. And we use the adjective anti to describe the relationship between the two hydrogens. The hydrogen in the front that's blue is gauche. The word that we use there is gauche to the hydrogen in orange here. The torsional angle between those two hydrogens is 60 degrees. And we call that relationship gauche, which I think is a French word for left. And it's true that this hydrogen is on the left side of the hydrogen, and the orange hydrogen is on the left side of the hydrogen in the back or in the front, whatever. But the pink hydrogen is also gauche. So go figure, I don't know. So gauche and anti are two words to describe the relationship between groups on the front carbon and on the back carbon. Anti is where they are 180 degrees apart. Gauche is where they are 60 degrees apart. Notice that any group in the front is gauche to two things and anti to one thing in the back. And that is what we call a staggered conformation. And the staggered conformation is more stable than the eclipsed conformation. If we do the same Newman projection of the eclipsed conformation, what you would see is the CH bonds in the front are perfectly lined up with the CH bonds in the back. Now we can't draw that exactly, so I'm going to draw a little bit of an offset, but when you see something like this, that means that it is in an eclipsed conformation. The two blue hydrogens have a 0 degree torsional angle and they are eclipsed. And this is higher energy because of electron-electron repulsion. Yes?
So are the gauche and the torsional both kinds of dihedral angles? And you guys agree with
Yeah, sorry. Torsional and dihedral are synonyms. And I'm sorry, I will use both of them. And I most of the time will use dihedral just because that's what I'm used to. Torsional and dihedral are both two words that describe the relationship in angle between two lines or two vectors. There's a technical definition, but we don't need to worry about that. So gauche and anti are both torsional or dihedral angles. Okay, and the fact that the staggered conformation is more stable than the eclipsed is an example of torsional strain. There is another explanation for why eclipsed is less stable than anti. It has to do with something called eclipsed is more stable than staggered. Oh my gosh. Thank you. There is another explanation for why staggered conformation is more stable than eclipsed. It's explained in your study guide. We're not going to talk about it a lot today, but it will be an important explanation in the future. The concept is hyperconjugation, and it's a favorable interaction where a filled orbital on the carbon in the front overlaps with an empty sigma star on the carbon in the back. And it's not a full-on interaction, it's a partial interaction, but we'll learn more about that later. If we were to plot these conformations on an energy diagram, what you would see is there is a staggered conformation where the two hydrogens that are triangled are 180 degrees away from each other. So there's one staggered conformation. There's another staggered conformation where they are 60 degrees away from each other, and then there's another staggered conformation where they are, I don't know, like minus 60, something like that. Okay? And minus 180 is the same as 180. So in between each of those is an eclipsed conformation. And you can imagine traversing this energy landscape from valley to hill, down to valley to hill, down to valley to hill, as you rotate those two triangled hydrogens relative to each other. The difference in energy between the valleys and the hills is about 3 kilocalories per mole, and at room temperature there is plenty of kinetic energy to freely traverse that energy landscape. Okay, so now what we're, go ahead.
Is 3 kilocalories per mole for any type of molecule?
The barrier, 3 kilocalories per mole, will depend on how big these groups are that are eclipsed with each other. So let's start to answer that question by having you look at your quiz. It's fun. Yeah. Oh, come on, the stakes are really low. You can put your name on the paper and still get credit. Do you know my oldest son in 6th grade once put his name on the paper? He was distracted and he wrote down name in the blank beside the word name. So thereafter, his 6th grade teacher just called him name, which was kind of funny. Anyway, your task is to use what you've learned about Newman projections to draw for me 2 different staggered conformations of butane. One in which the methyl groups are anti to each other, and one in which they're gauche to each other. And then you're supposed to consider which one is more stable. Do that, and then if we have time, we'll talk about how rotation in butane happens. We'll look at differences. Go ahead.
And we're just including C2s.
Yeah, so butane has carbons 1, 2, 3, and 4. You're just looking down the bond between C2 and C3. Yep. So take 2 minutes to get started on that. You need some montage music. How you doing? Do you need a little bit more time? Okay. All right, let's see what you got. the place to start when drawing a Newman projection between two sp2 hybridized carbons is just to draw a generic staggered conformation. From our perspective here, it looks like if we put our face in the plane of the page, the methyl group would be pointing down. So just start with this, and then do this for the carbon in the back, and then you can fill in the various options. The methyl group would be here in the front, and then if I want to draw the anti-conformation, where does the methyl group go? Yeah, up on the top, good. And that would put everywhere else the hydrogens, okay? So importantly, the relationship between the two methyl groups is anti, because the torsional or dihedral angle between those groups is 180. For a gauche conformation, you keep the carbon, you can do this in multiple ways, but I like to keep the carbon in the front exactly the same. And then I like to take the methyl group in the back, and we're going to rotate it 120 degrees so that each of the substituents on the carbon in the back trade places. So the methyl group would end up here, and the hydrogens would end up there. Here, the relationship between the two methyl degrees is, between the torsional angle between the two methyls is 60 degrees or gauche. Okay? Which do you suppose is more stable? Anti. Why is it more stable? Less steric hindrance, less electron repulsion, less torsional strain. Remember, electron-electron repulsion and steric hindrance are used interchangeably. Those are the same things, and they are the cause of torsional strain. So, all right. And it may not be immediately obvious why those two methyl groups are sterically repelling each other in the gauche conformation. To show this, it's helpful to have a space-filling model. And so here is butane, and here is the anti-conformation of butane as we sort of outlined it. And then here is the gauche conformation of butane. Now, even there, it doesn't look like the methyls are bumping into each other, but if we make that space filling, you can see that they are. They're actually in touching distance. So that's repulsion, and that's why the gauche conformation of butane is less stable. Couple of things I want you to think about. Draw for me the, and this isn't on your quiz, but I think it's useful. Draw for me the high energy eclipsed conformation that would be the transition state between this anti-conformation. We'll call this staggered conformation 1, and we'll call this staggered conformation 2. Staggered 1 is anti, staggered 2 is gauche. Draw for me the eclipsed conformation that occurs in the transition between these two. Where would the methyl group be? On the carbon in the back, where would the methyl group be? What's it going to be eclipsed with? The hydrogen, right? And then the other groups are going to also be eclipsed with hydrogens. Okay? So this is the eclipsed conformation that we get in the transition between 1 and 2. And this is a high energy conformation. So we would go from staggered 1 through eclipsed 1 to 2, and then back down to staggered 1. Sorry, back down to staggered 2. Now, should this energy level be as low as this one? No, because you just told me that staggered 2 is less stable. So to make my drawing accurate, I probably, if I were drawing an energy diagram, probably need to move the energy well for staggered 2 a little bit higher than the energy well for staggered 1. Your book tells you what that number is. I don't care that you know what that number is, just that you know that having the two things gauche to each other is less stable. Now, I want you to make a prediction here. Presumably, there is a staggered 3 conformation, which looks like this, where the methyl group in the back is now on the left-hand side of the hydrogen, of the methyl group in the front. Do you see that other gauche conformation? Now, imagine the eclipsed conformation that would be between staggered 2 and staggered 3. Which groups would be eclipsed? Which groups would be eclipsed with each other in that conformation? Yeah, the methyls. I'm just going to draw that real quickly here. Do you predict that this eclipsed conformation would be better or worse than this one? Worse, right? Because now the methyls have to be bumping into each other. So it turns out that if this staggered conformation wants to become this one, it's not going to go this way through that high energy eclipsed. It's going to go back down the hill and over the other way. Okay. All right, we didn't have enough time for chairs today. We'll do that next time. Good luck, and I will see you Friday. Yeah, please turn in your quizzes up front. Put your name on them.